This video has really 6 parts to it. I recommend pausing the video, and if you're needing to take notes on these properties, there are 6 individual properties, and each one of my next few slides is going to go through each one of them one by one with an example, but I definitely recommend stopping the video and copying these down just so you have them as a reference. So if I have log of a times b equals log of a plus log of b. Now this can be for any value, so like for example log of 21, well I know that log of 21 is really the log of a couple of different things. It is log of 7 times 3, and that is the most basic way to break this down. And so what I can do is, based on this property up here, I have my a, which in this case is 7, and my b, which is 3. So I can re-break this down into log of 7 plus log of 3. Now if I had a table of values that told me the exact values that this was, then I could replace this with a decimal, the log of 7 with a decimal, and I could replace log of 3 with a decimal. This just happens to be one of those really special scenarios, and when we add those two numbers together, we'll get the same thing as log of 21. Now log of 210 is very similar to log of 21 in that it's just 10 times greater. So what we could do is we could rewrite this as log of 7 times 3 times 10, and then we could do log again. So this is log of 7, and we're going to apply the rule above 3 times, plus log of 3 plus log of 10. So each time we multiply by something, we can add it as its own logarithm. Same thing happens when we're dividing values. So log of a divided by b is equal to log of a minus log of b. Notice that the denominator is the thing being subtracted. So if I am doing this particular problem, this would be log of 8 minus log of 10. This is a really special property that comes up quite a bit, and notice that we've got stuff that we can do by hand. Notice that there's a log of 10 there, and this is a problem that we're actually going to finish to completion. But I have log of 10 squared. I could rewrite this, and I'm going to in fact rewrite this. The exponent number comes down here in front. So I'm going to rewrite this as 2 times log of 10. Well, log of 10 is 1, so this is really 2 times 1, or just 2. And we can see this if we really understand what log of 10 squared is. Well, that's log of 100, and you should know that that is 2, which is the same as everything we've already done. Now this log of 4, this is a little bit tricky, but you should start to notice things with things like 4 and 9 and 25, that 4 is really 2 squared. So this is really can be written as 2 squared, and if you on a test are not given what log of 4 is, but you are given what log of 2 is, you should be able to convert log of 4 is equal to log of 2 squared, or 2 times log of 2. And if you're given log of 2, then you should really be able to compute the value. So I think that that's 0.3101. But I could be wrong on that. That's just me guessing. Actually, I think, here, I'm going to erase that. It won't let me erase it, so I'm going to just cross it out. Won't let me cross it out either. I think log of 2 is equivalent to the number 0.3010 times 2, and this ends up being 0.6020. Yeah, that looks right. That looks more correct. But you would be given this value on a test, and I would expect you to just multiply the two numbers together to get the 0.6020. A couple other properties, log base b of b to the k, and log base b of 1. Now these are really kind of things that you just have to remember. What we really are going to go back to what does it mean to be a logarithm, or how can we rewrite these in exponential form? So if you watch the video about what is a logarithm, you will notice that I can rewrite these as what power of the base is that. So I would rewrite this particular problem, what power of b is b to the k? And you should be able to see, oh, well, what goes in the box? The box definitely has to be k. And similarly, we can think of, oh, b to the what power is 1? Well, anything to the 0th power is 1, but it really comes back to understanding what this means in exponential form. So this is one of the most useful logarithmic laws that you will use. A lot of scientists use this, and we will use it mostly in pre-calculus, but it is one of the most complicated to explain. So I'm going to essentially show you how to use it. Unfortunately, we just don't have enough time to go over the purpose of its use, or how it is effectively used. So if you notice, we have base to the power of log with the same base of x. And if I have a base and a log to the power of log of the same base, it's essentially the stuff that's inside. So if I have 10 to the power of log base 10 of 4, my answer is 4. And if I have 2 to the power of log base 2 of 8, the answer is 8. We can get into some more complex examples, such as 3 to the log base 3 of 2x. Well, it's a base with a log to the same base is 2x. Or we could do things like 9 to the log base 3 of 2x. Well, what is 9? 9 is 3 squared times log base 3 to the 2x, which would end up being 2 times the stuff inside, 2x, which is 4x. But this is definitely more of an excessive example, something that won't happen frequently. The main thing that you need to take away from this slide is that if I have a base and I have it raised to the power of log with the same base, my answer is the stuff inside. So 3 log base 3 of 2x is 2x.